So let's discuss the alternating series. So we have already seen that summation 1 by n diverges. Yeah, it's a harmonic series or it's a p series with p equals to 1 and it diverges. Now then the question is, what happens if we add and subtract the terms instead? So we are going to alternatively add and subtract. So you have minus, plus, minus, plus, minus, plus, minus. Let me draw a picture of this. So when I'm adding 1, let's just move in this direction and say, okay, we are moving 1. Okay, so this is 1. Then when I subtract, I'm going back what? I'm going back half. Right? When I subtract half, I'm going back half. Then when I add 1/3, I'm going 1/3 again here. Then when I subtract, I'm 1/4, I'm going back. Then so on and so forth. And you can see that this sum, so these lines indicate the sum, the length of the line indicates the sum. And you can see that the sum basically eventually stabilizes, means basically it's convergent. Yeah. So this is actually converges. So you see, because of the alternating sign, the series converges. So let's generalize this idea. So this will give us what is called as an alternating series. Note that until now, if you forget about the geometric series, most of the, for comparison test, for integral test, and for limit comparison test, we only focused on what kind of series? Only on positive series. So this is a series where the terms should alternate in the sign. That is very important. So to make sure about that, let Bn be a sequence of positive terms, and we are basically having b1 minus b2 plus b3 minus b4, so on. This series is called alternating series, or you can write it as summation minus 1 to the power n bn. So this series is an alternating series. So for that, to check if alternating series converges or not, we have the alternating series test. So here, in this case, summation n equals to minus 1 to n, power n minus 1 bn is basically b1 minus b2 plus b3 minus b4, right? So it's basically minus 1 to the power odd will give you negative, and minus 1 to the power even gives you positive, right? So that's the idea, that the sign keeps changing because of the power. So it's moving over odd and even numbers. So this is how it changes. So alternating series tells you the following. Series test. If you have Bn plus 1 is less than Bn. So this means that it doesn't oscillate. Means does not oscillate. Why is that? Think about a series where things are going, it's going equally front, but then after that it's going equally back. Then it will basically never stabilize to a value, right? It will oscillate. So what should happen is that the oscillation should die down, right? If the sums are basically, so what should happen? The oscillation should die down. So what we need is Bn plus 1 is less than Bn. And secondly, limit of n goes to infinity of Bn must be 0. So if that happens, then this series is convergent. And that is what the alternating series tells us. Okay. So let's look at an example. So test the following series for convergence. So first of all, you need to check is it alternating? Yes, it is. So it is a form summation n equals to 1 to infinity minus 1 to the power n plus 1 times bn, where bn is 1 over n. Now note that here we had a form of n minus 1, and here we had form of what? N plus 1. So is it okay? Yes, it is indeed okay. As long as they keep alternating, it doesn't matter. All right. The first one is positive or first one is negative, it doesn't matter. But in this case, you can exactly write it as minus 1 to the power n minus 1 as well. Okay. So Here, we are going to use alternating series test. Let's see whether we can apply the alternating series test or not. Now, first thing to see is that Bn is, so Bn is has to be positive. Is that true? Yes, it is. If you write it like this, Bn is greater than 0. Now, what about Bn plus 1? Bn plus 1 is 1 upon n plus 1. That is clearly less than 1 upon n, which is B. So first condition is satisfied, that Bn plus 1 has to be less than equal to Bn. Second condition, limit, so condition 1 satisfied. What is limit as n goes to infinity of Bn? This is going to be limit as n goes to infinity of 1 over n, and as n goes to infinity, 1 over n goes to 0. So both the conditions are satisfied. So therefore, from 1 and 2, we get summation minus 1 to the power n plus 1 divided by n converges. And the justification is what? Alternating series. Alternating series. Yeah, so this is the justification for it. Right? So it converges. All right, so let's look at the next problem. Summation n equals to 1 to infinity of minus 1 to the power n square upon n square plus 2n plus 1. So let's look at this series and decide whether it converges or not. So here, again, this is an alternating series, right? So A, your Bn is n square upon n square plus 2n plus 1. Now, sometimes you can use instead of checking the first one, why don't we check the second one, right? So if you check the second one, you'll see, what do we get? Limit as n goes to infinity of Bn is not 0. Yeah, therefore forget about the alternating series test. Therefore, by divergence test, so it diverges using what? Using divergent test. Yeah, we have already seen that before. Yeah, so you don't need to use alternating series test. Since limit as n goes to infinity of Bn is not 0, this is gonna diverge. Let's look at problem 2 now, B. So we have summation n equals to 1 to infinity minus 1 to the power n pi by 2 minus arctan of n. So in this case, we have what? Bn is pi by 2 minus arctan of n. Now note that how does the arctan graph looks like? So arctan graph is, so this is how roughly the arctan graph looks like. Okay, so these are the asymptotes, minus pi by 2 to pi by 2. Yeah, so you have that pi by 2 is always bigger than, so since pi by 2 is bigger than arctan n, for all n, we have pi by 2 minus arctan n is greater than 0. Why do we need this? Because first we need to establish that it's a genuine alternating series, right? So Bn is greater than 0, therefore this is an alternating series. Just because it's an alternating series doesn't mean it will converge, right? We have to check whether it satisfies the condition for convergence. So this is an alternating series, right? So that's one. So now we need to see if is Bn plus 1. So question then, is Bn plus 1 less than Bn? Yeah. Is it true? How do we show that, right? Or in other words, is pi by 2 minus arctan n plus 1 is less than pi by 2 minus arctan of n? Or is it true, that arctan of n plus 1 is bigger than arctan of n? And the answer is yes. Why? Because look at the derivative of what? Arc tan x. That is 1 upon 1 by x squared. Now you'll say, well, so what about it? So this is greater than 0, right? Therefore, arctan is an increasing function. Yeah. So therefore, what do we get? So therefore, what do we have? We have arctan of n plus 1 is bigger than arctan of n. But then by that would mean that this is true. This would mean this is true. So therefore, bn plus 1 is less than bn. So first thing is fine. Now we need to check what is limit as n goes to infinity of bn. That is same as limit as n goes to infinity of pi by 2 minus arctan of n. And we already know that this is an asymptote. So pi by 2 is an asymptote for this guy. So limit as n goes to infinity of arctan of n is pi by 2. So pi by 2 minus pi by 2, which is 0. So therefore, bn equals to 0 as well. So from 1 and 2, therefore, by alternating series test, this series converges. So by alternating series test, this series converges. So now we are interested in the following. So you have this alternating series, and suppose it converges to S. So since it converges, we have bn plus 1 is less than bn, and limit as n goes to infinity of bn is 0, right? Then we want to basically make a, so if we basically find Rn, what will be the bound on Rn? What do I mean by that? So S minus Sn is your Rn, right? This is how the Rn is defined. So absolute value of Rn is going to be absolute value of S minus Sn. And then the idea is that that is less than equal to bn plus 1. So this is an estimation of this guy. So now use this fact above to find out e to the power minus 1 accurate up to how many decimal places? 4 decimal places. So let's see, what does this problem means? This problem means that we want it accurate up to 4 decimal places. Yeah. And not only that, we want to compute e to the power minus 1, given that e to the power minus 1 is this series. So how do we go about it? So first of all, we need to see how many n's do we need to compute. So we have Rn. In our case, we want it accurate up to how many decimal places? We want it accurate up to 4 decimal places, right? So accurate up to 4 decimal places means the first 4 decimal places must be what? 0, right? Then it will be accurate up to 4 decimal places. So we want Rn to be 0.001. We have that. And so we want Rn, the error has to be less than this. Then we'll get accurate up to 4 decimal places. So now we want, that means what is bn plus 1? Bn plus 1 is 1 upon n factorial. We want 1 upon n factorial to be less than, this is our Rn, We want 1 by n factorial. So we want this to be less than bn. So we want this to be less than 1 upon this one. So let's see. First term is 1, second term is 2, third term is this. So it has to be less than n factorial, not n plus 1. So what n factorial gives me, so that means what I'm looking for, I'm looking for n factorial greater than 1 upon 0 0.000001. That means I'm looking for 1 followed by 1, 2, 3, 4, 5. So I'm checking for n factorial. When does it becomes bigger than 100,000? Okay, so let's check that out. So let's see, what is 8 factorial? 8 factorial is 40320. That is not bigger than this. What about 9 factorial? So if you do 9 factorial, so I have to use calculator for this. So 9, so 9 factorial turns out to be, yeah, 9 factorial is big enough, right? Because it's 362,000. So if you take n equals to 9, we get 9 factorial is bigger, which is 362,880 is bigger than 10000. So in this case, our n is 9. So what are the terms we need to compute? So therefore, our term we need to compute is, we have to go all the way until 9. So we have e to the minus 1 is roughly, we get roughly equal to 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial plus 1 by 6 factorial minus 1 by 7 factorial plus 1 by 8 factorial minus 1 by 9 factorial. So this is your sum. Okay. So whatever the value is.